introduction. So the main target of these studies were myopia. Well, myopia is also called nearsightedness or short-sightedness. And if you compare like a myopic eye to a normal eye, what we would see is like under myopia, the eye is getting longer, and this causes the focal spot to be in front of the retina. And the retina is actually the place where the light is detected, and this leads then to blurring of the vision. Well, and we are in particular interested in the sclera of the eye. So the sclera is the outermost layer of the eye, or it's also like the white part of the eye. But the sclera somehow is giving the eye the shape, and it's like a viscoelastic structure, and you have to consider the eye to be like a fluid-filled sphere that is constantly under pressure, and the sclera is holding this in place. Well, and you can already easily imagine that if something is changing to the shape of the eye, it must be related to changes in the sclera. And indeed, studies shows that myopia is related to scleral thinning, so the sclera is getting much thinner. We have decreased collagen synthesis, increased collagen degeneration, and also other studies shows it's more flexible and less load-bearing. So definitely the material properties of the sclera play an important role in myopia. So, but how can we investigate changes of the material properties, in particular just of scleral tissues? Well, there's different approaches that has been proposed. So, for example, you can do strip extensometry, where you basically put the sclera, fix them like on clamps like this, and then you just pull on the sclera, and by this you can measure like elastic modulus. Or you have like inflation testing, where you just pump the eye with some fluid, and you measure like how the eye is inflating. And you can also do acoustic force microscopy, which gives you also information of elastic modulus at this very small spots. However, we want to do acoustic microscopy, and what I'm stating here is like all these methods are actually more complementary rather than competing with acoustic microscopy. So you can easily imagine this will give me, for example, only the elastic information of the whole sclera instead of really the material properties, the intrinsic material properties of the tissue. So therefore the aim of this study was to use quantitative acoustic microscopy to study the material properties of the sclera. Well, so for this study we used a form-deprivation myopia model. So the animals had to wear like a light diffuser on their right eye, and this the animal tries to adapt to the change in the vision, and therefore can induce a very high myopia. And the animals were sacrificed after 14 days of life, and then the refractive error and axial lengths were measured. And in order to measure them with the acoustic microscope, the eyes were then embedded in OCT and snap frozen. And then we took cryosections with a cryotom of 12 micrometer thickness. And we took sections at different locations of the eye, so like at the central axis, at the nasal edge, or like directly at the optic nerve. While directly before measuring, the sample slides are put into saline to ensure rehydration of the slides and complete thawing. But this is our acoustic microscope that we developed for these experiments. So basically, the sample slides are connected, mounted on this two-dimensional scanning stage, and we are measuring here in a so-called upside-down configuration. So the sample are attached to the glass plate, and we go from underneath with the ultrasound transducer, and by scanning we can derive two-dimensional maps of the material properties of the sample. We use a 300 megahertz pulsar from geosonders, and we scan with a step size of about 2 micrometers. And the RF data is digitized with 12-bit resolution at 2.5 gigahertz sampling frequency. And this is the transducer that we use. It's a special, very highly focused 250 megahertz single element transducer with a sapphire lens provided by the Fraunhofer Institute. And the transducer provides a very high bandwidth of 160 megahertz, which allows us to separate the signals in time to measure speed of sound. You see, like, this is one glass plate reflection here, and this is the power spectrum. Well, and, as I mentioned, it is very highly focused, so the beam width is about 7 micrometers, which gives us the lateral resolution. However, the focal depth is very high in order to give the high resolution even for the 12 micron thick sections. Well, let me also quickly introduce a little bit the signal processing that we have implemented here. So basically, for these experiments, you can only consider 2 locations. One location where we get a reflection from the glass plate, and one where we have our sample. And at this location, we would expect to get 2 reflected signals, one from the sample surface interface and one from the sample reference material interface. Well, and the idea here is to model these reflected signals. Going too fast. Model it by a summation of 2 of our reference signals, and these signals are just modified in amplitude and shifted in time, and also modified by an attenuation term. Well, what you can show is if you just take the Fourier transform of this model and divide it by the Fourier transform of our reference signal, then you can come up with this term, and you see that it's automatically changing. I'm sorry. And you can see that this term is mainly determined by this cosinus term, and the frequency, it depends directly on the time difference of these 2 signals. And you can also see that based on this model, you can also derive the amplitude coefficients very easily. And if you do some model fitting, you can also derive the attenuation. So to summarize, with this technique, at one measurement, we can derive the thickness of the samples. And from this, we can derive speed of sound, the amplitudes of each signals. And from the amplitudes, if we have calibrated reference signal, we can also derive the acoustic impedance. Well, and as I mentioned, we can derive also the attenuation from this method. Well, acoustic impedance and speed of sound together give us the bulk modulus and the mass density of our material. Well, the bulk modulus somehow relates to the stiffness of the material, so you can consider it like if you would have like a constant change, unit change of pressure on the material, it would say like how the volume of this material will change. And so that means higher bulk modulus means a stiffer material. And this is like just showing like a result one. This is like the reference signal, this is the measured signal, and using this model, you see that we can very well fit our signals to this model. So it demonstrates that the model that we use here is valid. Well, and these were the first results. So this shows like acoustic property maps, in this case the bulk modulus at several locations. So we have like here these are sections from the right eye, these are sections from the left eye, and you see like these are like sections through the nasal edge, so you don't see the optic nerve here. These are sections directly the midline where the optic nerve is, and you can clearly see the optic nerve here. And what you already see here like is a huge variation of the acoustic properties within these samples. So for example, it looks like the optic nerve, the tissue is a little bit softer than when you go a little bit further away from this location. Well, and for one of these samples in this preliminary study, which shows the highest myopia, what we found here, if we look at the inferior part and the superior part of the eye, you can already see here, if you compared at the healthy eye, so the left eye, and you see there is a clear difference in the material properties of the sclera. Well, and this effect is not that obvious in the treated eye. And this just put it into some numbers. So these are like really like just initial results. We just put some region of interest at this sclera, and then just analyzed some values. So you see, like here, these are the average values that we derived for all of our samples. And what we found here for this very high myopic case is that the inferior part indeed showed significant higher values in all acoustic properties, like it's stiffer, we have denser, we have higher attenuation, and speed of sound, and the acoustic impedance. However, if we compare it to the treated eye, we don't see a difference like this. And however, if we look just at the inferior part, like the lower part of the eye, and if we compare the treated eye with the control eye, then interestingly we found that the bulk modulus, speed of sound, and acoustic impedance is decreased for the treated eye. But these are interesting results, and the question now is how to interpret this. So for the guinea pigs are actually animals that are living on the ground, and the inferior part of the vision is basically responsible for far seeing of predators, and the upper view of the eye is more like responsible for seeing objects that are closer. So it is actually natural that the superior part of the eye is more myopic than the inferior part. So to conclude, in this study we derived acoustic property maps of the guinea pig, and we saw significant regional differences, and it is likely that myopia is not just affected to related to structure changes like the cortical, the scleral thickness, but also to the intrinsic material properties. But of course, we have to evaluate more samples in the future, and we also want to assess different scleral layers. So for this, I want to close it. This is we also recently got a 500 megahertz transducer, and which would provide a higher resolution. So maybe we can also assess different layers of the sclera. This is like the optic nerve here, and we see like the retina. And we can even resolve now almost the rod and cones in the retina. And thank you very much for your attention.